Picture this: a swamp at midnight. The air is thick, humid, and buzzing with insects. Somewhere in the darkness, something massive moves through the water, silent, patient, and hungry. This is the Florida Everglades, and it has a problem that no one saw coming decades ago. A problem that now stretches across 1.5 million acres of wetlands and has swallowed entire species whole. The Burmese python. And Florida's answer to it? A robot dressed up as a rabbit. This is not science fiction. This is not a joke. This actually happened. And what followed was one of the most chaotic, costly, and ultimately eye-opening wildlife experiments in American history. To understand why Florida was desperate enough to build robotic rabbits, you have to go back to the beginning. The 1980s and 1990s were the peak of America's exotic pet obsession. Reptile shops across the country were selling baby Burmese pythons like they were goldfish. They were beautiful creatures, dark, patterned scales, calm temperament, and small enough to coil around your wrist. People love them. But Burmese pythons do not stay small. Within a few years, that cute little snake becomes a 15-foot, 100-pound constrictor capable of swallowing a deer whole. Owners panicked, and instead of seeking professional help, many simply opened a back door, walked to the nearest canal or swamp, and let the snake go. Others lost their animals during natural disasters. In 1992, Hurricane Andrew tore through South Florida with catastrophic force, destroying reptile breeding facilities and releasing an unknown number of pythons directly into the wild. Those snakes found paradise. The Florida Everglades offered everything a Burmese python could ever want: warm temperatures year-round, endless wetlands, dense vegetation for hiding, and an abundance of prey that had never evolved to fear a giant constrictor. Raccoons, rabbits, foxes, marsh birds, none of them knew to run. And because the python had no natural predators in this new environment, their population didn't grow. It exploded. Today, conservative estimates put the invasive python population in South Florida at somewhere between 100,000 and 300,000 individuals. Some researchers believe the true number may be even higher. The ecological damage is staggering. Studies have documented population crashes of over 90% in some native mammal species across areas where pythons have become dominant. The Everglades food web, one of the most complex and delicate ecosystems in North America, began quietly collapsing from the inside out. Florida did not sit back and watch. Over the years, wildlife authorities launched initiative after initiative to control the python population, and almost all of them ran into the same wall. The first major public push came in 2013 with the Python Challenge, a state-sponsored hunting competition that drew enormous media attention. Thousands of volunteers registered, lured by cash prizes and the excitement of tracking down one of nature's most formidable predators. They fanned out across the Everglades with airboats, headlamps, and machetes. Weeks passed, and after all that effort, the final count was 68 snakes. 68, out of a population that potentially numbered in the hundreds of thousands. The math was brutal. Authorities then professionalized the effort. The Florida Python Action Team Removal Program hired licensed hunters who knew the terrain and worked at night when pythons are most active. These teams were skilled, dedicated, and highly trained. But the Everglades is simply too vast and too wild. For every snake removed, countless others were breeding, nesting, and thriving deeper in the swamp. Officials even tried a strategy called Judas snakes, fitting captured female pythons with radio transmitters and releasing them back into the wild, hoping they would lead hunters to breeding aggregations. The idea had a certain clever logic to it, and it worked sometimes. But the sheer scale of the landscape made consistent success impossible. A snake wearing a tracker can still disappear for weeks in 1.5 million acres of swamp. It became clear to scientists and wildlife managers that brute force, no matter how well organized, was not going to win this war. Something fundamentally different was needed. The next major innovation came from a surprising direction: the nose of a trained dog. While humans can only spot a python if it happens to be visible, a dog can smell one. And the scent signature of a Burmese python, a faint, musky chemical trail left in the soil and vegetation, can linger long after the snake has moved on. Florida Fish and Wildlife Conservation Commission researchers partnered with canine training specialists to test whether dogs could reliably detect hidden pythons in field conditions. 2 dogs were selected and trained intensively for months. Truman, a black Labrador retriever, and Eleanor, a Dutch shepherd, learned to identify the specific scent profile of Burmese pythons and alert their handlers when they found it. The results were remarkable. In controlled tests and early field deployments, the dogs were detecting pythons that trained human teams had walked right past. In one documented case, Truman located an 8-foot Burmese python in a remote area of Miami-Dade County in a matter of minutes, a snake that had evaded human searchers entirely. The dogs were estimated to be dramatically more effective at detecting hidden pythons than human hunters working without canine assistance. But scaling the program was an enormous challenge. Training a single detection dog takes months and significant financial investment. Maintaining a dog team in the brutal conditions of the Everglades, temperatures regularly exceeding 100 degrees Fahrenheit, alligators, venomous snakes, razor-sharp sawgrass, requires specialized equipment, veterinary oversight, and careful logistics. To cover even a fraction of the Everglades meaningfully, authorities would have needed hundreds of dog teams. The budget simply wasn't there. The dogs proved something important, though. Scent was the key. If you could find the right way to exploit a python's sensory world, its ability to detect heat, its chemoreceptive tongue, its instinct to pursue warm-blooded prey, you might be able to turn those instincts against it. That insight led a team of engineers and wildlife biologists down an unusual path. Rather than searching for pythons across an impossibly large landscape, what if you could draw the pythons to you? Researchers initially tested this idea using live marsh rabbits, a natural prey species for Burmese pythons, housed in secure protective enclosures placed along known python travel corridors. The results were immediate and striking. Pythons appeared with surprising regularity, drawn in by the scent and warmth of live animals. The concept of lure-based trapping appeared to have genuine potential. But the images that emerged from those field tests caused an immediate backlash. Photographs and video of terrified rabbits surrounded by massive constrictors went public, and the response from animal welfare organizations was fierce and sustained. Funding dried up under the pressure. The live bait program was shut down before it could be fully evaluated. Faced with this setback, the research team made a decision that would define the next phase of the experiment entirely. If they couldn't use a real animal, they would engineer one that was close enough to fool a predator. The result was what the team informally called the Robo-Rabbit. These were not simple decoys. They were sophisticated machines built to replicate every sensory signal a Burmese python uses to detect prey. Each unit was covered in synthetic fur and housed an internal thermal system that maintained a surface temperature of approximately 99 degrees Fahrenheit, nearly identical to the body temperature of a live marsh rabbit. Since pythons are highly sensitive to infrared heat signatures and use heat-detecting pit organs to locate warm-blooded prey, this was a critical element of the deception. Beyond heat, each robot emitted a chemical scent compound engineered to mimic the natural musk of a marsh rabbit. Some models incorporated small servo motors that produced subtle physical movements, a twitching ear, a shifting nose, just enough to suggest the presence of something alive. Solar panels provided continuous power, allowing the units to operate independently for weeks at a time. Hidden inside each robot was a suite of monitoring technology, motion-triggered cameras, thermal imaging sensors, and wireless transmitters that sent real-time data to researchers stationed miles away. Each unit cost approximately $4,000 to produce. 120 of them were manufactured and prepared for field deployment. The deployment began with cautious optimism. The robotic rabbits were anchored inside protective enclosures across known python hotspots throughout the Everglades. Within the first 48 hours, alerts started coming in. Field cameras captured footage that seemed to validate every hour of engineering work. Large pythons, some exceeding 15 feet in length, approaching the decoys with clear predatory intent. They flicked their tongues in the air, reading the chemical signals. They moved toward the heat. And then instinct took over. They struck and coiled around the robots, as if they were genuine prey. Field teams responded quickly, and snake after snake was captured in those first days. Then day 3 arrived, and reality arrived with it. An alert triggered from a unit positioned near a deep canal. The team monitoring the feed expected to see another python approaching. Instead, they watched a 12-foot alligator moving through the water toward the enclosure with purposeful speed. The robot was emitting exactly the same signals the alligator was wired to respond to: heat, movement, the suggestion of vulnerable prey. The alligator hit the enclosure with explosive force. In a single snap, a $4,000 piece of precision engineering was destroyed. It was not an isolated incident. The robotic rabbits were not broadcasting signals that only pythons could read. They were sending out a general invitation to every apex predator in the Everglades. Alligators, it turned out, were far more aggressive and far more efficient at locating the units than the pythons were. Dozens of robots were systematically destroyed over the following weeks. The pythons, for their part, seemed to respond to the presence of alligators near the decoy sites by avoiding them altogether. The same predator-prey dynamics that play out in nature were playing out around the experiment, and they were undermining it completely. From the outside, the project looked like an expensive catastrophe. Officials began discussing whether to pull the plug entirely. That's when a young data analyst on the research team noticed something that changed everything. While the robots had largely failed as physical traps, they had been extraordinarily successful as surveillance instruments. Every unit, including the ones that had been destroyed, had been recording and transmitting data throughout its operational life. Movement events, thermal readings, timestamps, directional approach data, behavioral sequences. And when the full dataset from all 120 units was compiled and analyzed together, a picture began to emerge that no one had anticipated. The pythons weren't moving randomly across the Everglades. They were using specific routes, consistent pathways through water channels and sawgrass corridors that they returned to repeatedly. These weren't random wanderings. These were deliberate travel patterns, shaped by the need to avoid alligator territories, move efficiently between hunting grounds, and reach nesting areas. Hidden highways through the swamp, invisible to the human eye, but perfectly clear in the accumulated data. Researchers fed everything they had into a machine learning system. Every movement event, every behavioral observation, every environmental variable recorded by the field units. The AI began to process patterns at a scale no human analyst could manage alone. And it started making predictions, not just about where pythons were currently active, but about where they would be at specific times, under specific temperature and weather conditions. The system had learned to anticipate python behavior by identifying the environmental triggers that drove their movement decisions. The hunting strategy changed completely. Instead of waiting at decoy sites and hoping for encounters, teams began moving to intercept pythons along their identified travel corridors at predicted high-activity times. Instead of finding isolated individuals, they began finding groups. And by specifically tracking the movement data of large, mature females, the AI helped lead researchers to something that had never been systematically located: